So, hello again, everybody, and today we will start talking about receivers, and of course we will be interested in optimal receivers, the receivers that produce the minimum error probability. Well, basically speaking, those receivers who make mistakes less often, right? That's of course, naturally, the most interesting case for us. Of course, you must realize also that it's more complicated and challenging way to make a receiver, but we are ready to pay that price. So, at the beginning, we will talk about how we can generate the signals for each of the modulation types: binary amplitude shift keying, binary frequency shift keying, and binary phase shift keying. After that, we will at once have our third practical exercise on making those signals in MATLAB Octave. And then we will talk about how to decode, detect, demodulate those signals and read data. And afterwards, we will do a practical exercise about that too. Those two practical exercises are closely related, meaning that you will need results of the practical exercise 3 to work with practical exercise 4. So you can actually format them as a single report. You don't need to make separate report for exercise 3 and separate report for exercise 4. Instead, you can merge them into a single report, and that will count as both of those practical exercises. But I will return to that later when maybe more people will come. And now let us start talking about modulators, about blocks which we need to create our radio signals from logical levels of 1 and 0. So, and the simplest way is the amplitude shift keying, binary amplitude shift keying, which is technically simple. Also, it provides some economy of energy conservation, right? These are pros, advantages. Also, of course, there are cons. And the main disadvantage is that the noise immunity, meaning the error probability, right, is the worst for these modulation types. So this modulation will make mistakes most often compared to other two options, which we will check today. So how can we generate binary amplitude shift keying signal? First, we must understand logically how it works. The idea is to convert logical 1 signal to harmonical oscillations waveform of some specific carrier frequency of 0. That is our carrier, of which we have talked previously, that we can use different frequencies for different systems. We use certain frequencies for Wi-Fi, certain frequencies for radars, and for GSM, and for GPS, and so on and so on. All these different systems have different carrier frequencies, which most often are currently around 2 to 5 gigahertz for modern communications. Also, of course, we use higher frequencies such as 10 gigahertz and even 80 gigahertz, but that is more for network operators and satellite communications rather than usual people like us who are using some devices, right? So that is the signal for logical 1, and for logical 0, there will be constant 0 voltage level. So that is the idea how binary amplitude shift keying signal should look like. So let's see the picture, which you have undoubtedly seen multiple times, but now I'm reminding you this picture, that indeed for a logical signal 1, we have some harmonic signal, which is in our case sin function. Basically, it can also be a cosine function and some random phase trigonometric function, but this is trigonometric function anyway, right? And well, for 0, we have 0 level, and so on. And that's where our energy economy comes in, right? If you transmit 0, then you don't waste any energy to send this silence period. And that's when you can keep some of the energy. Now, of course, it's arguable if this is worth it compared to, for example, frequency of phase manipulation, which provides better noise immunity. But anyway, there is such option to consider, which is always nice. So, also, we can basically speak that in binary amplitude shift keying, we are putting this logical symbol as a factor before this signal. So in this case, we are multiplying this signal by 1. And in this case, we multiply this signal by 0, the very same signal. And that's why this is called amplitude shift keying, because actually our data goes directly into the amplitude of the harmonic signal. You can say that this 0 level is actually a harmonic signal with a 0 amplitude, right? So this way it comes together, and that's our amplitude modulated signal. So how can we generate that signal? Obviously, we need some generator which is providing us harmonic signal. This is carrier signal, and we need some piece of hardware, some generator, which generates that signal. This is constant signal without any pauses, interruptions, and so on, from 0 to infinity, or at least as long as we don't turn it off, right? Here is our data at the second input, which basically turns on and off some switching device. This is our some kind of switch, electronic switch, which can be operated by a voltage level. For example, a transistor. That's the simplest device which can be used as this switch. And the idea is very simple. If this switch is unconnected, then this generator cannot send its signal at the output, and therefore we get 0 level at the output. When data is 1, the switch is closed, and the generator signal can pass through that switch until this switch is again open, right? So this provides these bursts of the harmonic signal, which are then amplified. This is our amplifier, and sent to antenna. And then from the antenna, it's transmitted further. So that's quite simple and easy way to generate the signal. Of course, if we are going to make our simulation, then we will need some other way for this switch. And basically, mathematically speaking, this switch works like a multiplication element. As I have showed you, you can multiply 0 with the signal and get 0, and multiply 1 with the signal and get the carrier signal fragment, right? So in our simulation program, we are going to use multiplication instead of switching. But for electronic components and schematics, we are going to need some kind of the switch. And as I have told, the simplest way to organize this schematic is to use a transistor. Basically, this U signal, this data signal, can have only 2 values, right? So this transistor is going to be either open completely, either completely closed. And this resonance contour is a part of a generator. So you can imagine that here we have some generator, and this resonance contour is just a part of this generator, which generates the signal with required frequency. So you maybe know that the resonance frequency depends on the values of these 2 elements. That would be square root LC, right? And if we choose different LC elements, then we get a different carrier frequency. So the idea is quite simple. And at the output of this resistor, we have the modulated signal. So that's the basic and the easiest idea how we can make amplitude shift keying signal. Now, of course, we usually nowadays don't use the resonance contours directly. We use instead quartz elements, which are denoted by this symbol and this abbreviation, right? Quartz crystal. These quartz crystals have the equivalent schematic of the resonance contours, which includes both series resonance contour here and parallel resonance contour here. So basically, this resonance frequency, this contour has two resonance frequencies which are very close to each other and can be calculated effectively as a single one by calculating this equivalent capacitance from this schematic. The quartz crystal is good because it has some piezoelectrical properties, which mean that if you have this crystal deformed by some physical force, then it generates signal. And it also works either way. If you provide some voltage to this crystal, then it deforms physically. This works as an inertia for the properties because, well, if we talk about resonance contours, they have a bad property that they have these components which parameters depend on the temperature. So imagine you are turning on that generator and your parameters for this temperature have been such and such. Now your schematic works, it generates some heat, these parameters temperature rises, and capacitance and inductivity also change. So that will change the frequency as well. So this is a problem of the frequency stability. Frequency stability, right? Which is low for this contour. Now, for the quartz crystal, however, this piezoelectric effect works as a compensator. So imagine that the temperature changes, so changes the frequency and changes the voltage, and then this change of the voltage tries to reshape the form, physical form of this quartz crystal, which of course will prevent that, will try to keep its own form. It has some inertia. So basically, this resistance to changing the form will put back our signal to the frequency where it should be, right? So this works this way. That is why we are commonly using these quartz crystals today in our any devices, including even the simplest watch which you use on your hand, in your mobile phones and so on. And well, that works nice. They are also very compact, unlike the induction spoils, right? You need some physical wire. Well, you need some base, then you need to make some wire spoils, right? And then that, of course, takes some physical place. These elements are quite big. We are trying to minimize the size of any device currently, and that's where these small crystals work very nice. They are actually some microchips which we can put in small devices, and they also work they work as also more stable. So it's indeed a good finding for us. So the generator itself is basically the amplifier used with a positive feedback network. So let's spend a few minutes talking about how actually we can generate the signal. The idea is, of course, to use some resonance contour or quartz element which is frequency selective, right? So this contour or quartz device will tell the resonance frequency of our signal. And then we need to feed some energy into this resonance contour at a regular time intervals because, well, in our physical world we all actually have everywhere some losses, right? Some resistance in this contour, some resistance at the input of the amplifier, I mean output, right, at the input of the amplifier and so on. And well, that's where our energy drains. So we need to provide the energy at a regular time intervals for this resonance contour by sending some short pulses. This works like some bell which you hit and then you hear the sound, which slowly fades, right? So you hit again and that fades again. In order to reduce this fading, we are going to use this amplifier. But this amplifier at the same time will change the phase of our signal, which will be needed to change again. So here we have some short video how this amplifier works for a few minutes. Let's check it fast out. So the idea is here is our amplifier and here is our feedback network. And you send to amplifier signal with certain frequency. This amplifier improves the strength of the signal, but also changes its phase. It is an inverting amplifier by 180 degrees or by P. Then this feedback network needs to change for another 100 degrees the signal phase, and it circulates again and again, right? So the idea is quite simple. We are trying to maintain the signal, and well, that's where we make that signal reusable, let's just say so. And well, this is the basic idea of how generator works. Now, this video will also show what's inside this feedback network and how it works. So for amplifier, in this part, we are going to use just a single transistor, but you can of course use also operational amplifier. But for feedback network, you can see that this is actually some kind of filter consisting of capacitors and resistors. So here our phase after this first capacitor will change by 60 degrees. Each capacitor will change the phase by 60 degrees. So total for 2 capacitors is 120, and for 3 capacitors is 180 degrees, right? And this amplifier itself will also change the phase by 180 degrees additionally. So basically this will return to this signal, which then will be sent again here, and so on. So this cycle will continue and continue. So hopefully now you will have some idea how these generators work. Okay, so we can go further for binary frequency shift keying. For binary frequency shift keying, now we need to put the information into the frequency here or here. So basically our signals matching the logical levels must differ in frequency. So the approach is pretty straightforward. We generate signals of 2 different frequencies, one for one logical level and another signal for a 0 logical level. However, here you need to select frequencies carefully, right? You need to provide the orthogonality property for these 2 frequencies. We have talked about that before. What are orthogonal signals? And here, in order to provide the maximum distance between these 2 signals, which is important for receiving and the error count, we need to have these signals orthogonal. The orthogonality condition defines the difference between these 2 frequencies. So basically, for these signals to be orthogonal, their frequencies need to differ by this delta F. It's not really relevant what exactly is F1 and what exactly F2, as long as this difference satisfies the condition that it's divided by 2 symbol durations, where T here is the symbol duration. For example, you have in your course project this parameter, right? And k is any integer number, 1, 2, 3, and so on. If this condition is satisfied, then these two signals are orthogonal. And that's exactly the case we are going to use for binary frequency shift keying signals. Now, if we draw this signal, then it also looks like a frequency manipulated signal, meaning that for signal of the value of 1, we have one value of the frequency, and for the signal value of 0, we have another frequency, right? So it's quite easy to visually notice the difference between these two frequencies because we have selected quite a large value k. So if we would put, for example, k equal to 1, then this plot wouldn't be so visually observable. So basically here we have k equal to some kind of 8 or maybe 12 and so on, right? So that the difference between these frequencies is actually noticeable by eye. But it would be just as orthogonal for any integer value k as for which has been selected for this plot, right? So as long as the k is integer number, we are doing fine. So the generation itself now includes two switches and two generators. Obviously, we need one generator to generate F1 frequency and another generator to generate the signal with frequency F2. Of course, we will now speak how we can simplify these, because having two generators is not really good, because each of these generators is subject to its own instability, and it would be much better if this instability would be same. However, if these blocks are separate, two different devices, then there is no way we can find these blocks in a such way that they would have same instability. So that's the purpose, to merge them somehow into a single source, and then they would share the instability. But in the simplest way, we have two generators, each of them generating harmonic signal with different frequencies, right? And we have two switches, which work, let's just say, in an opposite way. So meaning, if this switch is open, then this switch must be closed. There is no way that these switches are both open or both closed at the same time because of this inverting element, right? So if we send here 1, then 1 will close this switch, but after inversion 1 becomes 0 and it will open this switch. If we send 0, then it's opposite. This switch is open and 0 is inverted to 1 and this switch is closed. So basically one of these switches is always closed and another is always open, right? So this basically connects output to either this generator or this generator. And that's how our frequency shift keying signal is created, right? So you can actually say that this is BASK 1, first amplitude shift keying generator with one frequency, and this is actually the second generator, BASK2. And that's exactly how we will make our mathematical model of this signal in our practical exercise. So we'll generate two BFSK signals and sum them up together in this point. Afterwards, it's also amplified and sent to antenna and channel. Now, there is a way to generate these two signals from a single source with high precision, quartz element inside, and so on. For that, we are going to need some frequency dividers, which reduces frequency to some factor. For example, here we have, let's say, 100 megahertz. And then we divide it by, let's say, 40. So at the output, we are going to have 25 megahertz frequency for the signal. Then we multiply this 25 megahertz signal by its frequency, not signal itself, but we multiply its frequency. So these are specific microchips capable of changing signal frequency, right? So for example, in this case, we would multiply that by 4 and have here 120, no, I mean 100 megahertz, right? And here we will multiply by 5, which is 4 plus 1, and have 125 megahertz. So that way we have obtained from a single source 2 different frequency values. And that's actually how it's working in our devices, including your mobile phone, because, well, mobile phones actually can use very large number of different frequencies, and you need to convert frequencies from a single source. So basically, that's where we are using so-called frequency synthesizers. So if you are interested, you can look up more information about these synthesizers and how they work. Basically, then they can change n from 1 to some kind of, I don't know, to 1,000, right? And generate 1,000 different frequency signals at the same time, which can be then used in your signal processing in any way necessary, right? Also, there is even simpler way to change the frequency of the generator is to use a varicap diode element. As you know, varicap diode has some barrier capacity which changes based on the voltage you have applied to this varicap. So the idea is quite simple. Your data is 2 levels of different voltage, which then sets 2 different levels of the capacity for this varicap, which is included with quartz crystal into resonance contour, and this generates different frequency, right? So basically, this generator with varicap is itself modulator. You don't need any extra switches and anything else, right? So basically, data signal changes capacity, capacity changes frequency, and the frequency output also, well, generator outputs different signal, right? So this is voltage controlled oscillator, VCO for short, which itself is a frequency modulator. And finally, binary phase shift keying, which is good in a way that it provides the highest possible noise immunity, meaning that the PR probability is actually minimum of what we can ever hope to achieve if we do everything correctly with the receiver, right? However, this requires some high precision synchronism, right? The idea is that the information is hidden inside this initial phase. So when we have harmonic signal received, as it will turn out later, at the receiver, you need to generate precisely the same initial phase signal. So, for example, let's just say this signal will not really do because we have some shift here. And you need to make this shift close to 0. That's where this is problem from synchronizing. Also, additionally, there is a problem that if you are calculating the square of this signal, you will lose this sign information, and there will be no way you can tell if it's 1 or 0. Because imagine that you have minus sin squared and you have plus sin squared. After calculating this square, there is actually no way to recover that sign, and meaning the information itself, because here we have 0 as plus and 1 as a minus. Or consequently, this 1 can also be considered as the phase shift for this signal P, which, according to school geometry formulas, actually gives us the minus sign of the same initial phase of 0, right? So that's how it's working. And that's, well, both good and bad, because this actually requires some very precise operation, which currently at the modern day we are capable of, and we can do that. But anyway, we use these phase shift keying only in the case when we have very low signals, such as in the space applications, such as the slowest Wi-Fi operation mode. It also includes binary phase shift keying for the case when you are quite far away from your router, because, well, which modulation is used for Wi-Fi actually depends on the position of your router and your device. The further you are away from that router, the slower data is sent, but the safer at the same time. So basically we need to increase noise immunity, and as a last resort for the limiting distance, let's just say so, we are using binary phase shift keying. And after you move away even further from your router, there is nothing that can help you to receive that signal better. So you need to get back into the coverage area of this router to get stronger signal and higher data rate. So for binary phase shift keying, the information is hidden inside the initial phase. So here we are transmitting 1, and our SYN signal starts from positive direction, right? For 0, our SYN is from the negative direction. Actually, when you add noise to this picture, and that's what we are going to do in our practical exercise 1, you will see that there is no way to see by eye where is the 1 and where is 0 anymore. However, in our second part of the lecture, we'll talk about optimal receiver, which can extract that information, given that you will provide exactly the same original signal to compare with. So basically the idea is you will have this signal as some kind of template, some original signal which you can use to compare what you have received with what you could have expected. And you are doing this for each symbol. But we'll return to that when we talk about receiver. So how can we make this phase shift keying signal? Basically, since we don't have to use different frequencies, we are bound to use the same generator. And once again, we need to change the phase. So basically we change by 100 degrees the initial phase. So here is the inverter, the analog inverter, same as operational amplifier, which changes the phase of the signal. So here it's plus SYN signal, here it's minus SYN signal. And in the same way as for binary frequency shift keying, we are operating these two switches, which cannot be open or closed at the same time for both. So either one of them is open and the other one is closed always, right? It only changes, well, which one is open, but there is only one open switch at the same time. We are not considering any delay in this element also, right? So this is a logical inverter, which converts 1 to 0 and 0 to 1, vice versa, right? But there is also another way to generate the signal, is to use NRZ coding for your data. So if you convert your data from zeros and ones to NRZ format, which is represented accordingly by +1 and -1 levels, then you can just multiply your SYN signal, and, well, where you have +1, you will have plus SYN, where you have -1, you will have minus SYN, then amplify it and send to antenna. So that's how we are going to make that in our practical exercise. Here I'd like to once again mention that there is most often the assignment for NRZ is performed as 1 is converted to -1, and 0 is converted to +1. Of course, it's not really important, but this assignment provides us additional benefit for XOR operation. You already know that XOR operation truth table looks like this. So if we have zeros at the input, we have 0 at the output. If any of the inputs is 1, we have output 1. And if both inputs are 1, then we have 0. So that's XOR truth table. If we assign according to this, then XOR can be replaced by simple multiplication. So let's see. We have assigned +1 to 0. So if we have +1 multiplied by +1, we would indeed get +1. Now, if any of the symbols to be multiplied is -1, only one of them, or either this one or this one, then the result is also -1. Now, if both are -1, the result is 1. So as you can see, these two operations in this case are equivalent. So basically here we have 0, 0, 0, which is this. Here we have 1, 0, 1, which is this. Here we have 0, 1, 1, which is this. And here we have 1, 1, 0, which is this. Now, if we would assign it differently, that wouldn't work. So let's see. So now, assume that we are going to assign +1 to 1 and -1 to 0. Then, assigning here, right, for 0 -1, after multiplication with another -1, we would not get -1. So these operations won't be equivalent any longer. So that's why we assign in this particular order, right? So I just wanted to make that more clear to you why I am using this particular assignment, right? Although, as I have said, you can still assign differently, but you need to remember how you have assigned for your receiver, because that will be important to select correctly the comparison sign. Either it's smaller or greater, just as it has been in the practical exercise 2. In the same way, we will have to make that choice in the practical exercise 4 today. So that is for lecture part about transmitter EAT. And now we will have a short break of 10 minutes. Afterwards, we will have a practical exercise number 3, where we will try to make these transmitters, these modulators, in MATLAB. All right, and we'll add noise to the signal. So see you in 13:25. Right, and then we will start working with Octal.